hearing me? No. So this. Okay. Can you hear me? Yes. Okay. First of all, I want to thank the organizer of this beautiful conference for inviting me. And yes, in this talk, I will present you some new results we obtained in the Dysprosium lab in Pisa. Okay, this is not. Where basically we could observe supersolid properties in a dipolar quantum gas. So let me first introduce you briefly what is supersolidity. So supersolidity is, let's say, a counterintuitive phase of matter which combines in the same single component material solid and superfluid properties. So at the beginning, supersolidity was predicted by this series of seminal work by these important guys, and it was thought in the context of solid helium-4. In this material, in fact, the zero-point motion of the atoms is very large, and the system can basically have some vacancies which, let's say, can flow as a liquid inside it. And at low enough temperatures, this gas of vacancies can Bose-Einstein condensate, creating, let's say, a superfluid flow inside this solid material. So this was the original proposal, and for many years, people looked for supersolidity in solid helium-4, but this was without success because of many reasons. Actually, what this experiment tried to measure was a decreasing of the momentum of inertia of solid helium-4 by decreasing the temperature of this material. This was observed, but could not be, so it was never, let's say, unambiguously related to the supersolid properties of this kind of material because of many technical reasons, because of the presence of impurities, dislocation, etc. So still, up to now, it's not clear if supersolidity is, let's say, could be observed there. This is not known. But at the same time, people started to think about different materials, different, let's say, environment where supersolidity could exist. And basically, this environment are always made of gaseous Bose-Einstein condensates, which are naturally superfluid, with some kind of long-range interactions. So some kind, yes, of long-range interaction which should allow some density modulation in this kind of material. So here you have some examples of the system where, let's say, supersolidity was proposed. And I have to say that in 2017, two systems, spin-orbit coupled atoms and atoms in optical cavities, let's say, revealed themselves as good system for having supersolidity. Actually, supersolidity was observed there. For example, this is an example of the ETH experiment done by Tobias, where a supersolid state of matter was observed. Actually, this supersolid is a particular kind of supersolid. In fact, it is perfectly stiff, so in the sense that the solid part of this supersolid is not compressible. Okay, a different kind of system where supersolidity could exist are dipolar quantum gases. So dipolar quantum gases are just quantum gases where the dipole-dipole interaction is strong enough to be considered. So in this system, the interaction energy can be written as a sum of two terms. A term is, let's say, the standard contact interaction, which is short range and isotropic. And the second term is the dipole-dipole interaction, which is long range. It scales as 1 over r cubed. and anisotropic, so two dipoles are repelling themselves in this configuration and attracting themselves in this other configuration. So in our system, in our experimental apparatus, we have a dipolar quantum gas. We just use Bose-Einstein condensates of dysprosium atoms, which is the most magnetic atoms available in nature. And in this system, the dipolar interaction parameterized by this ADD, it's of the same order of the contact interaction. And actually, we can also tune the strength of that contact interaction by using Feshbach resonance, as in standard cold atom experiments. So we can change the strength of, let's say, the relative strength between dipolar and contact interaction. And we can enter in regimes where the dipolar interaction is much larger than the contact interaction because we decrease the contact interaction. Okay, so now let's consider a gas, let's say a standard, let's say a dipolar gas in a standard trap. And let's think that this trap is an elongated trap in this x direction, and the most confined direction of this trap is along the dipole alignment. So this L0 is the most confining direction, which is in the direction in which the dipole are aligned. So in this case, the excitation spectrum of the system is peculiar. It was studied kind of 20 years ago by Santos and co-workers in this seminal paper here. And as you can see, the excitation spectrum, let's say the long wavelength part of the excitation spectrums, it's linear. It grows like in standard Bose-Einstein condensates. So we have phonons. In fact, for this wavelength, the dipolar part, let's say the important part of the dipolar interaction is just the repulsive part. But then by growing the momentum, let's say the momentum k of the excitation, at some point, the attractive part of the dipolar interaction starts to contribute to the excitation energy, and we have a decrease of the excitation energy, which leads to a minimum in the excitation spectrum for some peculiar k, which is of the order of 1 over this confinement there. So in this case, we have a Roton, and the question is, what happens to a dipolar gas when this Roton gap goes to 0? So in our system, we can actually tune this gap here by tuning the strength of the contact interaction. So we could actually, in principle, bring it to 0. What happens when this Roton gap is nulled? So this was studied in a nice experiment by Francesca Ferlaino in Thyssenbruck. Actually, they observed then when, let's say, the Roton gap touches 0, a Roton instability occurs in the system, and you can see that two side peaks appear in momentum distribution close to the k equals 0 peak typical of a Bose-Einstein condensate, which means that the density modulations develop in the system with a certain periodicity, which is exactly the Roton periodicity. So the question that arises there is this system, let's say a stable system, is this state a stable state, or at least a metastable state? What happens at long times? This is just the signature of the Roton instability. Is this just a Roton as an instability, or is this bringing the system to something stable, something that is not going to collapse? And actually, in quantum gases, what is known is that quantum fluctuations are really important because, let's say, the mean field part of the energy is actually the sum of two mean field terms, the contact interaction and the dipolar interaction. They are both large terms, but they have different signs. So in this sense, quantum fluctuation cannot be neglected, and they have to be accounted for describing the ground state energy of the system. So the Lewin-Yang term, which is accounting for quantum fluctuation, is always there. While the mean field energy can mean smaller than 0, this Lewin-Yang term is always positive, and it can stabilize the system. It actually always stabilizes the system. So depending then on the atom number, we can have stable Lewin-Yang gases, or also, let's say, some strange system which are quantum droplets, basically self-bound states stabilized by quantum fluctuations. So these droplets were observed 3 years ago now. Basically, if you see this picture, you can ask yourself, are these supersolid, no? So are these supersolid? It came out that in this case, they were not supersolid because these droplets are too deeply bound. So they are too far, so phase coherence is not preserved here. But our question was, can we put together Roton instability and quantum fluctuations and, let's say, observe something which has supersolid properties, something which has a density modulation because of Roton instability, but also, let's say, phase coherence because of the overlapping weakly bound droplets. So that was our question 1 year ago, more or less. And we tried to investigate this problem with our tools, so with an experiment. So basically, this is our experiment. It's very simple. We just have a dipolar Bose-Einstein condensate inside an elongated trap. You can see that the most confined direction is the Z direction, which is 81 hertz, which is the direction where the dipoles are aligned. And then we have a weak direction where the Roton instability develops. So all the measurements are done in time of flight. So I will just show you, let's say, picture of the momentum distribution of the atoms after free fall. And these are our, let's say, main results, at least for the first part of the talk. So here we were just studying the time evolution of our system for 3 different contact interactions here. So this means for 3 different dipolar strengths of the condensates. So here above, you just have a standard BEC. So here the system is just like a normal Bose-Einstein condensate, which is evolving during time. But as soon as we decrease the contact interaction, we basically enter the Roton instability regime. And what you can see here is that also in our system, 2 side peaks appears close to the k equals 0 peaks, signaling the emergence of a density modulation in our system. What is interesting is that this configuration is there for a long time. So we observe this, let's say, Roton, let's say this stable stripe for a long time, at least for 50 milliseconds. Then eventually the system decays into a BEC, but we don't have a lot of thermal part around it, signaling that maybe this system is coherent. Then I will show you further studies on this. If we instead decrease further the contact interaction, we enter in a second regime, which is more confused. Here, the, let's say, interference pattern is very incoherent, and every shot is different from the other. So we call it like incoherent droplets. So let's see more, let's say, more quantitatively, what are these stable stripes that I'm showing you there. And for doing this, we have to analyze our momentum distribution. So this is done just by using a double slit model. From this double slit model, we can get information on the depth of the density modulation, which we have in C2, which is this A1, on the periodicity of the density modulation, which is the K rot, let's say the periodicity, and most important on the phase of, let's say, of the relative phase of the different droplets in the initial density distribution. Here you have an example where the relative phase is 0. Here you have an example where the phase is instead by half. This is the phase of the interference pattern. What we did to study the coherence properties of the system was just to, let's say, to stay at a fixed time and then to analyze the phase distribution of the interference pattern which we were recording. And as you can see here, at least at 20 milliseconds, we had a distribution of the phase which is not uniform. It's peaked around one value, which is 0. So we can say that here, at this time, at least, we had some phase coherence inside our system. This is done for more than 50 images. So we repeat these measurements at longer time. You can see that the 30 millisecond situation is very similar. So we still have some phase coherence. While if we wait more, up to 70 milliseconds, at some point we recover this uniform distribution of the phase, which is signaling that we are losing phase coherence in the system. This is what is plotted here. I'm just plotting the, let's say, the width, the variance actually of these histograms here. And you can see that we have some phase coherence in our system up to at least 30 milliseconds before losing it. And at some point, the variance just get the uniform random phase. Okay. Another way that we have to, let's say, probe phase coherence, less quantitative, but okay, still it's fine. It's just to sum up different images, and this is what we did here. So this is the coherent stripe regime. You can see that we still observe at long time this pattern this stripe pattern, which is signaling that this phase is preserved here, while in the incoherent droplet case, at short already, we don't have any phase coherence. We cannot recognize any pattern. Okay, so this is what is telling us that what we are observing is really the signature of a supersolid, of a metastable supersolid properties in our dipolar gas. Actually, to support our experimental investigation, Russell Bissett and Luis Santos came out with some realistic numerical simulation of the system. And basically, these numerical simulations are done at finite temperature, including the Lagrangian term, and including also three-body losses. I didn't mention it, but we have strong three-body losses in our system, so we lose atoms during time, and that's also why we lose phase coherence, probably. And actually, what they observe is something very similar to what we observe. So here you have the two Ks, coherent stripes and incoherent droplets. You can see the density distribution here, and above you can see the phase, the evolution of the phase. You can see that in the stripe regime, the phase is maintained for a long time, actually much longer than what we see. And in the droplet regime, instead, the phase is lost. Let's say the coherence on the phase is lost immediately. So let's say, then maybe we can enter in more detail later. But what this is meaning is that, let's say, what this theory is saying is they are basically confirming that what we are seeing is something which is coherent for some time and then loses its coherence properties because of losses. But the system is coherent, what we are observing. So it's, let's say, a transient supersolid state. So this was done, let's say, I have to say that this kind of experiment were also done by the Innsbruck group, V group, and by the Innsbruck group and the Stuttgart group, and they also observe very similar feature, which is actually very good because basically they are confirming our observation. Okay, and so they are confirming the existence of a metastable supersolid state in these dipolar quantum gases. Okay, up to now I just show you the existence of this, let's say, peculiar phase of matter. It exists something which has a density modulation in the dipolar quantum gas and which preserves phase coherence, but I didn't say anything about symmetry breaking, and I didn't say anything about the excitation modes of this kind of system, so I didn't characterize it still. And this is what I want to show you in the second part of my talk. If we go back to the, let's say, to the original paper from Andreev and Lifshitz of 1969, they already speak about here the acoustic properties of this supersolid, and they say that two kinds of motion are possible in the supersolid. One possesses the properties of, let's say, of the motion of an elastic solid, let's say phonons of a solid, and the second one possesses the properties of the motion of a liquid. So this means that in our system, two sounds velocity should be there, and we should observe them already, so also in our, let's say, transient system, at least at the beginning. In other words, let's say we can say that every time that a symmetry is spontaneously broken, a Goldstone mode can arise, and this happens in the superfluid where the gauge symmetry is broken. We have phonons here, but this happens also for the solid where the translational symmetry is broken. We can have the solid phonons. In the supersolid where we break both gauge and translational symmetry, we should have two branches of the excitation spectrum, which should be linear at k equals 0. Okay, the question now is how to observe this kind of excitation spectrum in our system, which is a finite size system. So how can I map, let's say, phonons in a system which has, let's say, a bound dimension? I have a minimum dimension, which is the confining trap. And the answer to this question is that phonons can be mapped onto the compressional modes of the system. So if I have a system with a final length Lx, there is a minimum momentum of my excitation which is proportional to 1 over Lx. And this means that there is also a minimum excitation energy of the system which is proportional to the velocity of sound times this k mean. And this comes out to be of the order of the, let's say, of the frequency, let's say the confining frequency in this direction. So this was studied long time ago, let's say at the beginning of the Bose-Einstein condensate era, where when actually, for example, this was studied both experimentally and theoretically, I have to say. So there are nice experiments by Ketterle and Cornell where they were measuring the collective excitation of a Bose-Einstein condensate. In that year, Stringari was developing this, let's say, the hydrodynamic equation for an ideal liquid for the case of a Bose-Einstein condensate in a Thomas Fermi regime. So here you have the order parameter of the Bose-Einstein condensate, and you can relate the gradient of the phase to the velocity of this liquid, and the modulus of the order parameter to the density of the liquid. And if you solve this equation in a trap, you can find that the compressional modes are the solutions of this equation. Actually, the condensate is excited at discrete energies, and you can find monopole mode, dipolar mode, quadrupole mode, etc. So in some sense, these compressional modes of the BEC are a consequence of the locking of the phase of the condensate, so the gauge symmetry breaking in a condensate. Okay, this was studied theoretically also for a dipolar quantum gas. The picture doesn't change in a dipolar quantum gas. You can see here a picture. Let's say this is just the evolution of the mode energies as a function of the dipolar parameter. So this is the case where there is no dipolar interaction. We just have standard modes studied by Stringari. By increasing the dipolar interaction, this energy slightly shifts up to some point where the system is strongly dipolar and one of these modes collapses. So one of these modes softens, bringing to the collapse of the system. Anyway, this energy is not changing a lot. So what we decided to do in our work, in our, let's say, new work, experimental work, was to study the evolution of this mode when passing from a Bose-Einstein condensate to a supersolid and see what happens there. And this mode is just, this is the lowest lying mode, just above the dipole mode, which has no compression inside. So the dipole mode is just a movement of the center of mass. This is the lowest lying mode, and it's just the axial breathing mode. So this is a mode where the axial direction oscillates out of phase of the two other directions. And the frequency of this mode, the energy of this mode in a BEC is expected to be, in a standard BEC, is expected to be square root of 5 the frequency of the trap frequency in this direction. So let's see how we studied it. In the BEC regime, this is very easy. We just quench the scattering length by crossing a narrow resonance. This problem is full of narrow resonances. So you can use it to quench your scattering length. And we just studied the evolution of the size of the BEC in the x direction during time. You can see we can have very precise measurements of the frequency, and we found that the frequency of oscillation, let's say the frequency at which the BEC oscillates, confirms the theory, also the dipolar theory actually. But how to study this system in the supersolid phase? So here the experiment is less trivial. So what we did for beginning was just to run a numerical simulation. And I have to say the theory was done by the Trento group, Roccuzzo, Recati, Stringari. So what they did was just a numerical simulation at t equals 0 in the absence of the losses. And what you see here is the case, let's say, is the oscillation of the axial width in the case of a BEC up there for a supersolid and in a droplet regime. You can see that the BEC is oscillating normal frequency square root over 5 while in the supersolid regime something strange appears. Here we have a beating, the evidence of a beating of 2 different frequencies. This is very nice because this reminds us that in the supersolid phase we should have 2 sound velocity, 2 speed of sound. And these 2 frequencies could be really related to these 2 speed of sounds. So the bad news is that this is due to the couplings of these 2 sound modes. Basically, this effect is there just for very small amplitudes, which are less of 5%. I remind you, in our BEC experiment, we had amplitudes of 20, 30, 50%, more or less. So in order to try to observe it, we have to ask ourselves what is the nature of these 2 frequencies that they were observing in the theory. And again, we can, by, let's say, evaluating in the theory the time evolution of the distance between our droplets and the amplitude of our lattice, we can see that the higher frequency is related to, let's say, a movement of the droplets, let's say to an oscillation of the distance between droplets, so it's really related to the solid mode, while the lower frequency is related to an oscillation of the lattice that we are creating in our supersolid, so it's more related to the superfluid fraction moving around in our supersolid. So with this in mind, we can go to the experiment and try to measure not only the second momentum, the second moment of the momentum distribution, but also the periodicity K and the modulation depth A. These are things that we can measure. And if we look at that, we see that the second moment doesn't show a beating because, okay, first of all, I have to say that here we don't excite the system by crossing a flashback resonance. We just enter the supersolid transition and we observe this oscillation here. The second moment doesn't show a beating because this amplitude is too large, but let's say this periodicity K and this amplitude A shows instead two different frequencies, one larger and one smaller, which are the evidence of these two modes also in the experiments. So if we put everything together, theory and experiment, we can map both the BEC and the supersolid regime, and we really see that when we enter the supersolid, this conventional mode bifurcates in two, one related to the oscillation of the phone of the lattice, and one related with the oscillation of the superfluid. So with this I'm done. I have to say that similar experiments were done also in Innsbruck and Stuttgart, and I will just show you conclusion and outlook here. You can ask me if you want.
Okay. Thank you very much. Time for a few questions.
We have two quick ones. So the first one, the experiment of Francesca Ferlaino of 2018. Yes. So how is that different from yours? So why wouldn't